15 of ME370, Elements Mechanical Design. Here we're going to introduce the Distortion Energy Theory, DET, aka von Mises stress. All right, so this is section 5.5 in the textbook. We want to define this new stress. We're going to create a new kind of stress. That's going to be known as the effective stress, right? So you can think of this von Mises as doing one of the best jobs they can of trying to make condense all of the stresses into one single type of stress. It's also referred to as octahedral shear stress, and don't ask me why. But we mostly know it as von Mises, and then sometimes von Mises-Henke, to try to give somebody else that I think that he came up with the same thing like at a similar time. All right, so this originated from the observation that ductile materials, when they're stressed hydrostatically, that is like everything equal on all sides, right, either in compression or in tension, right there, that they were much higher strengths. The strength was much higher than if you just pulled in, like, say, in one direction, right, or if you just sheared the thing. So if you had all equal amounts of stresses, that a ductile material is much stronger than it would be if you just did it in a single direction. So it really decided that it was going to break strain energy, right? It was going to say there's two kinds of strain energy. There was this strain energy that you could think of as when everything on a cube is the same, right? You can think of it as a spring. It gets this is a kind of strain energy, right? It does squish when it's compressed equally on all sides. It would expand if it was pulled equally on all sides. Usually, typically we'd be compressing because it was much easier to do. So we'll describe that scenario. So we have hydrostatic volume changing strain energy. And then we had angular distortion, right? So, or distortion that brought the thing out of its principal shape, right? It was like if it's a cube starting out with, it's some other shape, or it's like a rectangle, or it's a rhombus or whatever. That is distortion energy, right? So you get the two kinds. So you have the volume changing energy where it's equal in all sides, and then you had this distortion energy. All right, so this is the theory that yielding occurs when the distortion strain energy per unit volume reaches the distortion strain energy per unit volume for yield in simple tension or compression of the same material. All right, so what did that just say? The answer is apples to apples, right? What we're gonna do is we're gonna find the distortion energy in our regular stress state and equate it to the distortion energy that occurs inside a pull test, which is where the yield stress comes from, right? So we get the yield stress from a pull test, find the distortion energy there, equate it to the distortion energy in a generic stress state. And what we do here is a little different, is that we invent a new stress. We invent a new stress by doing that. So we're going to show the derivation step by step, and hopefully it'll make sense. You can digest it, but then you can quickly forget it and just remember what the stresses are, I guess. But anyway, to make a nice little to equate things, right? To get a more insight into what this looks like. They're calling this octahedral shear, but this is the von Mises is the oval. Right here, we had the maximum shear stress theory right here was this hexagon, but you could see now that this let's call it an ellipse oval. It crosses at each of these little corners. You can see it's actually the same at all of those corners, but now it's a line, and the line goes pretty close to following through the data, right? Remember, these are all things that failed, right? These are different materials, and these indicate fail. So there are some that are on the inside, right? So there's a little bit of, maybe it's what we're going to find out is von Mises is very accurate right here, but it's not as cautious, right, as maximum shear stress theory. All right, so here's some concepts that we'll need to understand, or maybe things that you want to kind of think of, right? So imagine that a cube were placed at the bottom, the deepest part of the ocean, right? This little cube of ductile material, right? Steel, aluminum, something right there. If you could picture that, right? So now it had like an original shape of like this shape right here, right? It had that cube shape. But now the pressure is going to be the same everywhere, right? Because we're at the bottom of the ocean. Yes, it varies with vertical. It gets, you know, more and more as you get there. But we're really deep, so it's pretty close to being uniform everywhere, right? And so the thing is going to get like it's going to change its volume shape. It's going to get crushed, right? It's going to go on all sides. So what kind of stress would it feel? It would be compression, right? And if the stress is large enough, do you think the cube is going to fail? I mean, can you picture why it fails? Well, go back to what we talked about, the maximum shear stress theory. Wasn't it like on the slip planes? Weren't you? Wasn't the maximum shear stress theory kind of give us a picture that it's like the way that it's failing is grains sliding across each other? But how is that going to happen when everything is equal? Right? It's all just being crushed, right? If there are voids maybe in between the grains, they would collapse, right? But that's not really typical of a, especially of a ductile material. Right. So would it fracture? Would it fall apart? Would it turn into dust? Well, definitely not dust in the bottom of the ocean. It's too wet, right? But I mean, you got a picture like it'd be really hard to crush this thing. I mean, if you grabbed it, if Superman grabbed it in the middle and just squeezed it, yes, it would crush. But that wouldn't be equal on all sides, right? You can imagine that he's like kind of breaking the thing apart. So maybe you could get it in your head that like, that is a different kind of stress. That is that hydrostatic stress. And I always say, what do you think distortion energy is? I kind of already told you. I mean, so this is not a very good Socratic question here. But is distortion energy just like it sounds? It's the energy when something distorts, right? And when we're talking about energy, remember, we're talking about like strain energy, which is like a spring, right? That we've had a spring like right here just a second ago. Wouldn't you know, he disappeared. Oh, yeah, it's right there. So we got this little spring right here, and he's got energy, right? That's strain energy that's absorbed in the material and wants to rebound and come out right there. So distortion energy is when the thing changes shape that's not equal on all sides, right? And what is strain energy, and how do we find it? All right, so I've gone through this in a couple different classes, but I think repetitiveness is a good thing to do. Well, you could think of as strain energy as being like that thing, like, okay, so here's the tensile spring energy, right? So we have a pull happening right onto there, right? And we got stress because of F over A, right? And then we have this original length, boom. And then we have a del right there, so we have strain, right, which is going to be del over L. Well, one thing we could find right here is when we have a force that's being applied to something and we have a del, or no, we have like this stiffness of this thing, that right there, and we've derived that stiffness right in there. But one way that we could find energy, right? Energy, one form of energy, let's say, is work, right? Sometimes I use capital U for this, by the way, which is force times a distance, right? Well, here we go. Here's a distance. There's a force, and it's acting across a distance. So it has worked, and that is a form of strain energy. But in this case right here, we have this stress, and we have the strain, so we can see in a second right here. But here's the energy that we're doing if this thing was just a spring, right? And it would be actually, and it's actually it's the integral of F, let's call it dx, or sometimes we go dr right there, but it just means that the thing, and these have to be in the same direction right here. But anyway, integrating this right here, we end up finding that the energy is going to be 1/2 F times del squared. Just like what we had with potential energy, right? In dynamics, we had 1/2 K del squared. I said F squared, I meant K, sorry. because one of the things we know is that we have F, 1/2 F times D right there, and then we can replace F is equal to K del, right? So we could just replace that right in there. So that's where we're saying the potential energy, right? That's the strain energy that we're putting in from a spring. But when we talk about strain energy, another way that we could look at it is we have, let's see, stress over strain is with our elastic curve, right? With our material curve. Well, remember that this is equal to F over A. And remember that this is equal to del over L, right? In a simple test, right? So the energy that's below this thing right here, if we're going to talk about it, would be like 1/2 stress times strain would be 1/2 force times del A times L right there, right? So we have energy, and this right here, this would be just the volume, right? That would be the volume of this piece. So what we really have when we're looking at this area underneath the curve is a strain energy that's being absorbed when we load the thing up per unit volume, right? So it's energy per unit volume, just like what we had with our potential energy in a spring as it's being compressed. So the stuff that's inside here, of course, this is much more complex stress and strain state because this little spiral guy right there is actually shear stress that we mostly feel through that. We'll see in ME370 where we'll see like it's a fairly simple derivation to try to get this what the strain energy is in a spring, but we're talking about the simplest of stress states, and that's just a rod as an example right there. Okay, so there's your idea of strain energy, but now we need to go through this derivation because we needed that derivation for this. So let me get through these little guys right here. All right, so here you go. Here is our textbook derivation. So we always start out with a little cube, and we can say that this triaxial stress, right? So these are, and we converted everything into principal stresses, so we'll not worry about shear at this point. We've already converted principal stresses, so we have sigma 1, sigma 2, and sigma 3, all the principal stresses. Well, we could say, we could break that into two parts. We could say we have the average component, and that's going to be all sides have the same stress, hydrostatic stress. And then we'll say, well, what's the rest of it is distortion. That's the distortion component. So we say the stress is comprised of hydrostatic and distortion. So we want to get the total strain energy, just like I pointed out before. The strain energy, and this is per unit volume, once again, is 1/2 sigma times epsilon. But now we want to get the total, right? So we need all three directions. And we recall, by the way, this is just one example of three equations, right? And we could replace these x's and y's and z's. We could replace them with 1's, 2's, and 3's, right? So we just do that. So now we can get rid of the strain part of that because we get the equivalent of the strain in terms of stress. That's going to be nice for us, right? And then a little bit of hand waving, a little bit of algebra, and we're left with the total strain energy that's in this cube right here, right? That's just a generic thing. And we've not done anything special. We just, just like I defined what strain energy was, and now we've just gotten rid of the strain aspect of it. So now we have it completely in terms of stress and material properties. So we say Poisson's ratio and elastic modulus right there. All right, so move my big head out of the way. Now, this is just repeating that equation from the previous side. Now let's say, this is a generic formula for strain energy. What would it be if you only had the average part, right? Well, then we would take all three of the stresses and set it equal to the average stress. Say, well, we need to find the average stress. Here is the strain energy with average stress. Like that's the only stress that's applied to the thing. A lot of things cancel out right here, but we can condense this down to just 3 times this average stress, and divided by 2 elastic modulus times 1 minus 2 times Poisson's ratio, right? So we could do that algebra ourselves. So now we have taken and made this general strain energy thing into a specific kind of strain energy. Now we might want to like expand it out. Like, okay, so let's say if you wanted to find that same thing, but like, you know, now this is still the volume change, but all we've done is just replaced these back into it. You would see that this, you would kind of think that this would be like an unnecessary algebra step right here. But what it's done is really shifted from being like specific in many different ways to being generic, right? That we had the same stress condition. This thing is only true if all of these are equal to each other, but it still is true, right? So this is the energy to change the volume, hydrostatic stress only, right? So this is the condition when they're all equal, but this is the condition where you only find you only have the volume change stress. The volume change stress is right here. So this is the strain energy that's only due to the volume change. All right, so let's take that, and I'm going to reverse this thing right here. I'm changing. Well, I got to go back to this right there. You can see, this is the original arrangement. Now just flip it around. Now let's make it. We want to find the distortion part by taking the basic strain thing and subtracting out the hydrostatic. Right. So here's the total strain energy. Here's the volume strain energy. So if we subtract the two things out, one from another, we end up with this equation right here. And I've skipped the algebra, but that's the basic idea. Distortion energy is now equal to the total strain energy minus out the volume change. So we've subtracted out all of these things. You know, the principal stress is each one subtracts out from the other, right? So 1 minus 2, 2 minus 3, and 3 minus 1. And it doesn't matter what signs they are here because we square them, right? So we just wanted the difference between each of them and divided by 2. And then there's a material properties right in here. Okay, so this is something hopefully we've tried to buy the idea, the scheme that we're trying to isolate and just get only the distortion energy. All right, so here's repeating the thing we just found. Now, let's make a comparison. Like, what we think, what would be the distortion energy during a test, during a specimen test? Well, okay, that's just going to be, there's only going to be stress in one direction. So let's say just sigma 1. And that's going to be, and if it's at the point of yield, we would just replace sigma 1 and only sigma 1 with the yield strength. Right. This is the distortion energy at the point in a pull test, a simple pull test, when it's equal to the yield strength. Now set those two equal to each other. Right here, I went ahead and set them equal. Notice that these material property things are going to cancel out, and that if we wanted to get the yield strength, right, of this is the generics. This is just any type of stress a stress state being put onto the thing. Well, those cancel out, and we set a criteria. We say that this thing, when it's greater to or equal to the yield strength, that's when failure occurs. That's the distortion energy theory, right? That's when it occurs. But not only that, right? So this is right up to this point. It's very similar to maximum shear stress theory. That's what they're saying. By the way, this right here is the apples to apples component. This is when we're saying, okay, this is the pull test. Here's the distortion energy, and here's the distortion energy in a generic setup. And then we go, well, one step further, we can say, well, when all of this, you see this is the square root because this was squared. When all of this is greater than or equal to the yield strength, that's when failure occurs. So we could actually, instead of just saying it's equal to this, let's just say at any moment, what is this stuff on the left-hand side? We decide, we call that the effective stress. And that is von Mises stress. This is the definition of von Mises stress. Now, this is the most generic version of an equation for von Mises stress, but it remains true. But we really only need to use this when we have, let's see, I think I'll go to the next one. Let me continue on. All right, so let's just absorb that this is a very important equation here, and maybe I'll use the highlighter. Let's see. Let's highlight it. Let's highlight it. That's how important it is. Highlight, like kind of absorb it, kind of memorize it. but we don't necessarily need to do that. Now I ask this question, well, why are we doing this? It's an opportunity to make apples to apples. We see a little animation. Did that animation like improve our learning? I don't think it did, but I don't care. Say this is my little app. This is from my book, the Engineering Dynamics Course Companion. Have I plugged my book? I should plug my book. My books. See my 2 books? The Engineering Dynamics Course Companion. It's part 1 right here. There's me, Edward James Steele. Part 1 is particle kinematics and kinetics for dynamics. And here's my man Newt Dog and Wormy. These are my cartoons I draw. And then there's part 2 is rigid bodies, right? So we're full of dynamics examples for you and drawings, long worked out complicated formulae and problems. Example problems out the yin-yang. You really ought to buy it. Because nobody is, man. Anyway, all right, let's back to our thing. I mentioned, because I used my man Wormy right here. He showed up. From page 239, von Mises is the most widely used theory for ductile materials and is recommended for design problems unless otherwise specified. I read to you. You liked it, didn't you? And yeah, this tells you how important von Mises is. It is the go-to thing. Now, if you use finite element analysis, you'll know often if you hit solve and it pops up with the results, that's von Mises stress. And like, why would we use that? Well, for one thing, it's always a positive number. We don't have tension or compression in von Mises. Why? Because it's comparing itself to the pull test, to the place that we got the strength data. We got yield strength. We looked up yield strength. Where does that come from? That's only tension. So we just turned all the different kinds of stresses that there are, we turned it into one kind of stress, the pull test stress, because that's where the strength comes from. And we can compare them apples to apples after we've done that. Von Mises is great that way. And it's very, very nice when we're doing a finite element analysis, because we can have just one value, one scale from 0 to yield or whatever we want on the scale of the thing, but it's usually good to make it something sensible. And so the distortion energy safety factor is simply the yield strength divided by the von Mises stress, because the von Mises stress has converted the stress state into something that's equivalent to what gets done in a tensile test. And that's just makes perfect sense, and it's an apples to apples thing. All right, so here is our von Mises equation, our generic one. But we can reduce this and make it a lot easier to use. So first, this is in a 3 principal stresses, 1, 2, and 3. We've had to go find them. But we're mostly dealing with plane stress. We don't usually have 3 principal stresses. Well, at least one of them is usually 0. And in that case, we usually use sigma A and sigma B for the 2 principal stresses. And in that case, this right here, just algebraically, you can just substitute A for 1 and B for 2 and 0 for 3. And you can work this thing out. You'll find that it's A squared minus A times B plus B squared, and we're taking the square root of all that. So that's a simpler equation, right? Well, you know what? Maybe we don't want to find the principal stresses. Well, you know what we could do is we could just substitute in equations for principal stresses and see what happens, and someone's already done the algebra for you. And so this is the biaxial stress with some shear. Boom. There you go. We have an equation. We don't have to do the principal stresses. Someone has done it for you. So this is a really good equation to memorize. Unfortunately, it's not in the book. The next one's not in the book, excuse me. But one very, very common situation is we don't have biaxial. We only have uniaxial stress. We only have normal stress in one direction and then shear, right? That happens a lot. In fact, it happens way more often than biaxial stress, because so far we've only been able to create a biaxial stress scenario when we have a pressure vessel. On the outside surface of a pressure vessel, I should say. On the inside surface, we do have this top equation. We might need to use it for the inside. But for the outside, We only have we have that biaxial, but like for everything else, we pretty much just you have uniaxial stress. It's hard to get stress in that other direction, like right up here. We don't, it's only in that pressure vessel we were able to get, and that's because the hoop stress goes in the opposite direction, right? All the other stresses kind of align with each other. The bending and the axial and the longitudinal all go in the same direction, but it's only the hoop that goes like perpendicular to it. So if that's the case, we get this great equation. This is worth memorizing, but only using if you have uniaxial stress, which you do a lot, right? So when I was reintroduced to it, because I totally forgot about the existence of this stress until I started working at Electric Boat, and some of my coworkers said, "Yeah, well, we were doing some bolts, some things on the bolts. It was, yeah, but it's got a shear and it's got tension, so just use the von Mises." I said, "What, von who?" And they were like, "Yeah, this equation," and they were at this equation right here, and I'm like, where'd that come from? And so I opened up my Shigley because I kept my book. Dude, smart idea. Keep your books, kids. And couldn't find it, but I did find this one right here. That is in Shigley. They don't, maybe in example problems they will put this equation right here. But you'll notice if like y is 0, that goes to 0, and that goes to 0. So you can see that you get this one below. But it's short. It's easy to remember. So there you go. This is the go-to equation. Now there's one. I'll finish this up. This is the first part of the lecture. This is the introduction. Blah blah blah. Part. We'll do examples in the next videos. But let's ask. Okay, so what if there's only shear stress in this scenario right here? All right. So we just have something that's in pure shear and nothing else. Then sigma x goes away. So what if we want to say, okay, well, let's have a pure shear condition and find out what the strength is going to be? We would set it to this. So if we're rearranging this and we're saying, okay, well, this is the kind of, this is the stress at which the thing yields right here. Well, we could just say instead that this is the shear yield strength, 0.577. And that's really just because it's the square root of 3 that came from this part of it right here. We have to, maybe it would have been good to go through the algebra and show where that 3 comes from. It just, coming backwards through the process of replacing the principal stresses with the principal stresses equations that you would use, so that we could just start out with the xy, the sigma x, sigma y, and tau xy. If we just want to start out with those and not going through the process of doing more circle and finite principal stresses, someone's done the algebra for you, and that 3 falls out, right? So when we go to do this right here, and we want to say, okay, well, what if we don't have any normal stress, which is just pure shear? We're able to come up and invent a way. Now this is interesting. One of the reasons why this is interesting is compare this to the maximum shear stress theory. We have 0.5, right? So these are two competing theories into saying when the what is the yield strength in shear? Well, maximum shear stress theory says 0.5, and distortion energy theory says 0.577. This is a good number to keep in mind. All right, it'll come up, it'll pop up sometimes in looking at other specific things in ME370, right? When we look at later chapters of Shigley. So this is like a little bonus thing I'm putting into the video. I just created it. I don't usually put it in the notes or cover it, but I wanted to make a stress yield envelope Excel thing, right? So that I could plot it out and it could look real pretty. And asked a colleague when I was at the Coast Guard Academy, how could I plot this thing out? He goes, oh, you could plot it out parametrically. And I'm like, param what? And he described it. And it's not that. It's not rocket surgery. But let's use this equation right here, right? So this is going to be, because that's what we have in the stress yield envelope, or the failure loci, right? That's what we should be calling it. It should be called failure loci, not stress loci. Let's take on that graph, which uses sigma A and sigma B, let's just find the distance to a point by taking r and theta. So parametrically, the parameters, we're going to substitute the parameters of r and theta in order so that we can graph this thing, right? So it's just a sort of a little scheme right here. So we know that we could find the sigma a by taking r, whatever that radius was to that point, arbitrary point, and multiplying by the cosine of theta. We could do the same for sigma b. So let's just replace those inside this, right? Generic r right there. Well, let's solve for r now. Boom. Okay, so this, and I set this equal to sigma because we want a line, right? And that line is going to be a constant value, and that value is the yield strength. We want that to be the envelope onto the thing. So we do this, and we get this equation right here. So what we have is r as a function of theta, right? So here's a constant because we're going to draw a line with it. So what we do is now just the parameters. I just run a 0 through 360 because I want to draw the circle right here, and then I find the r for every value. So I just make a long column of thetas, and then I find what the r value is for a given yield strength, and then I go work out backwards. I back out what's sigma a at this combination of r and theta, right there. So you see it. So I just made, and I made it in radians, but these are, I think, like half degrees or something like that. I'm not sure what, I don't remember. I think I divided pi by 90, I think that's what I did. And so I think that's what the increments of radians are. But here is, for 0, by the way, this is for A36 steel. The yield strength is 36 KSI right here. So I can find at each of these angles, and so that really just plots this way around here. So it just plots all the way around this thing, and we're able to get it. So I've provided that to you in the assignments. You have something called the failure loci graph in Excel, and it wasn't hard to do, wasn't hard to make, but I made it for you already. And so that you can plot out the various, this thing right here. So I've made this. I've also made a second sheet for the Coulomb Moore here so that you can see. But all you need to do is change this, change that to 200. Boom. You can see all the scale changes, and then you only have to hit print and just hit print. Don't try to print and reformat. I already have everything set up, so whatever printer you have, this thing will come out. I can't emphasize how often students come up and only half the thing made onto the page. I don't know what they're doing that's making the thing print, like maybe they're hitting print screen or something. I don't know. But just go to print and hit print with whatever printer you're using, and this thing will come out. It'll be nice. It's and it's proportional too, right? So, but anyway, this is what I did right here, and but both things are on there. But I just took increments right here and see what. Oh, here's my increment. Yeah, pi divided by 90. So I just went from 0 and started adding that to the thing, right? So for every, I just kept adding it, and then I found the r, and there's that equation that I just showed you, and then of course I get the sigma a and sigma b, but it plots out this nice little oval so that you can use, and you can make a comparison, graphical comparison between the maximum shear stress theory and the distortion energy theory. And I think that's all that I had for this really long video. I didn't mean to make the video this long, but it is now 33 minutes wisdom. But here's an example we will do in the next video. See you then.